Academy of Sciences to deliver the first opening remarks on behalf of Nanjing University. Welcome.
Distinguished experts, esteemed colleagues from nature journals, and colleagues from Chinese Biology Society, ladies and gentlemen, in this pretty autumn season, it's our great honor to gather with scholars and scientists from around the world at the beautiful foothill of Purple Mountain of Nanjing for the grand opening of the Nature Conference, AI Augmented Biology. On behalf of Nanjing University, one of the co-hosts, I would like to extend a warmest welcome to all our guests, and my sincere gratitude also goes to friends who have long supported the development of Nanjing University. We are living a great era of transformation driven by data and algorithm. Just as the telescope and the microscope extended human's vision into the microscope and microscope worlds, artificial intelligence is now emerging as a new scientific research paradigm, reshaping how we explore the unknown with unprecedented depth and breadth. A profound scientific revolution has begun, where the intricate tapestry of life science meets the power of cutting-edge AI technology. From cracking the code of life to designing of novel drugs, from understanding the mysteries of evolution to constructing synthetic life, artificial intelligence is becoming the new engine for us to understand, modify, and even create life. Nanjing University is honored to co-host this prestigious event with Nature series of journals and Biophysical Society of China. This conference, I think, is more than just an academic exchange. It's a vivid testament to our collective effort to unite a global vision and explore the frontier of science. Concentrated on the theme of AI augmented biology, the conference brings together global thought leaders and distinguished scholars to discuss key topics such as multimodal data mining, protein engineering, the application of large language foundation models, the origin of evolution of life, and synthetic biology. We are confident that your insights and discoveries will ignite brilliant intellectual sparks here, inject a powerful monument into breakthrough process of the biomedical fields. As a 123 years old institution, Nanjing University has long been renowned for its excellence in science and established China's first Department of Biology over a century ago. In this new era, our university remains committed to its fundamental mission of serving for the nation, actively promoting interdisciplinary integration to address the frontier of global science and the needs of human health. We know that great scientific breakthrough often occur in the integration of intersection of the disciplinaries. As with conviction that as early as 2018, our School of Life of Science, with great foresight, proposed AI biology as a new academic discipline and began actively exploring its theoretical framework and practical pathways. Now we are delighted to see this pioneering concept has resonated widely across the global biological community, becoming a key factor force in advancing life science and laying a solid foundation for today's discussion. AI augmented biology, as its title itself is filled with infinite imagination for future. We sincerely hope that at this conference will be an opportunity for our expert scholars to inspire wisdom and deepen collaboration, jointly drawing a magnificent blueprint for the deep integration of AI and biological science. Nanjing University also eagerly to look forward to join hands with our global peers, guided by the principle of openness, collaboration, mutual benefit, to forge a forward-looking community for scientific innovation and make new and great contribution to advancing our healthy and well-being of tackling global challenges. Finally, I wish the Nature Conference AI Augmented Biology a big success. I wish all our guests good health, enjoyable exchanges, and with a fruitful staying at Nanjing. Thank you very much.
Okay. Thank you very much, Professor Zheng. Next, I'd like to introduce Professor Chenyu Zhang, the Dean of the School of Life Science at Nanjing University. Professor Zhang is among the pioneers who proposed the concept of AI biology as early as 2018. He also founded the Institute of AI Biomedicine at Nanjing University and the AI biology branch of the Biophysical Society of China. And under his leadership, Nanjing University has become a national hub for AI biology research. Please join me in welcoming Professor Zhang to give his remarks.
Thank you, Chao. And good afternoon, ladies and gentlemen, honorable speakers, dear colleagues and friends. On behalf of the organizing committee, it's my great pleasure and honor to extend my very warm welcome to each of you. Welcome to the historic city of Nanjing for the AI biology. And actually, I'm very excited about this meeting, and thanks for the nature teams across the ocean come over here. And also I want to appreciate all the sponsors and volunteers make these beautiful, great meetings. Also, I want to thanks for all the speakers from a very far distance from come to here and share very interesting and important, the research. Before, I would like to talk about or share some opinions about as an independent discipline. What is AI biology? It is not AI for biology. Okay, let me just see what's the AI biology. Forgive me, very ugly slides. Okay, And I just want to see the AI biology through studying the life emergence to find the biological intelligence. Therefore, if as independent discipline, they have two fundamental pillars is essential. The one is data, information, knowledge, and wisdom. The other one is life emergence. Okay, what is the DIKW? Data? Okay, I don't want to explain since I don't have much time. Information and knowledge. What's the life wisdom? Okay. Basically referring to the global capacity of the life systems to achieve goals, maintain stability, and adapt to the environment through multi-agent interactions. For the emergence, basically this is a core concept for the complex system. Basically, for the individual forms a complex system, they will have a new function and have the nonlinear interactions. They have properties that don't exist in the individual component levels. What's the life emergence? Okay, life emergence is a specialized form for emergence, referring special from the molecule to the ecosystem. In every layer, they will have emergence properties. And the life emergence is not merely structure. It is also functional. This is important. So, through this kind of DIKW models, AI biology moves from the raw data to the system level wisdom. And then the logical map is not only the methodological dimension, also in the object dimension. Okay, the important thing is with the AI biology discipline, the AI not only is the tools, they become the collaborator in the biological exploration. What's the difference? This is important. What's the difference to the other traditional disciplines like computational biology? This is important. Let's say this. The computational biology is how does life operate? The AI biology, how does life generate intelligence? For bioinformatics, the difference is the bioinformatics, what's the data? And the AI biology, how does life progress from simplicity to the complexity? And from the complexity to the intelligence? And what's the difference for the AI for biology? Of course, AI for biology is just AI is tools. And the AI biology lies theoretical innovation directions, blah, 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 blah. Okay. Summary. This is also important. Okay. And this kind of, I don't like the revolution. Basically, it's a cognitive paradigm shifting as an independent discipline. Okay. And finally, I just want to give you the example how to the AI biology studies. Okay, everybody knows the microRNA is just a trivial modulator for the individual microRNA studies, right? However, in this study, basically I put dysregulated microRNAs in the non-small cell lung cancer as a component to generate an independent autonomic complex system. This is data. And using AI, the AI is not so complex. Basically, using AI, we try to find these emergence properties of this complex system. Then we get the information. Amazingly, this changed or dysregulated microRNA, they have collective effect. In the non-small cell lung cancer, they inhibit tumorigenesis. Very surprising. And then, as we also studied the breast cancer, they also have a collective effect of inhibiting tumorigenesis. However, in the colorectal cancer, they promoting tumorigenesis. They become this become the knowledge. And then, what is the nature logic of inhibiting tumorigenesis in the difference basically in the lung cancer and the breast cancer? But in the colorectal cancer, there's a difference. This is the biological wisdom. We find, maybe this is a driving force for the tumorigenesis is different, and the stress is different. Well, we started. Basically, it's not so complex, but in the AI biology frame and the life emergence frame, we can find the very, the difficult problems right now unsolved, and find more important, phenomena to learn. Okay. So anyway, I don't want to spend a lot of time. It's not my. I'm not the speaker. So again, welcome to Nanjing. Welcome to the Nature Conference. Thank you.
Okay. Thank you, Dr. Zhang. As you all know, this Nature Conference has been in preparation for over a year, and with the tremendous efforts from the editorial teams across many nature journals. And the organizing team is led by Dr. Qian Cheng, the senior editor of Nature Communications, who will also serve as the moderator for our first scientific session. So without further ado, please join me in welcoming Dr. Cheng. Okay.
Good afternoon, everyone. A bit nervous, but very excited to see all of you today. I'm Chen, a senior editor from Nature Communications. On behalf of the entire organizing committee and my fellow editors from Nature Portfolio, I would like to welcome you all to the Nature Conference on AI Augmented Biology. It is my great pleasure to be here to start the conference with all of you, and thank you so much for being here today. We stand at a unique but exciting moment in history where AI meets the beautiful complexity of biology. We are now using neural networks to understand biological networks, and we use AI models to predict drugs or predict protein folds, and we'll be designing new therapeutics in the future. The conference is not just about a conclusion on what AI can do for us, but we also hope to build the collaborations that will define the future of both AI and biology, or as Professor Zhang suggests, the new subject area, AI biology. In the next 2.5 days, we'll bring you 28 key talks, 6 flash talks, and 38 poster presentations, covering a wide range of topics. So we really hope you will all find the conference interesting, productive, and inspiring. So now, let's get started. Okay, in the first session, we will cover the topics on the interface of AI and biomedicine. And our first speaker will be Professor Hoffen Poom, the General Manager of Microsoft Health Futures in the United States. And he will give us a talk on generative AI models for precision health. Let's give a warm welcome.
Thanks so much. Can everyone hear me okay? Awesome. Let's hope the AV will work. Where's the remote? So while we are setting up, so just want to say, so excited to be in Nanjing. I visited Nanjing many years ago when I attended the Chinese Math Olympic, and so it's so great to be back. So thanks organizer for inviting me and also organizing such an exciting conference in such a beautiful location. So it's so excited to see how AI become so popular these days. So I started my personal journey 2 decades ago in my PhD in machine learning and NLP. Back then, I would say AI was still in the last ice age. I have a friend who on the job market who literally had to disclaim that he was not working on AI. So it was a very different time. I joined Microsoft Research 15 years ago, and that was basically the 10-year anniversary of Human Genome Project. So at the time, I didn't know how hard biomed and health is, and so I decided to explore AI for precision health. So sometimes ignorance is about blessing. So in this talk, I would love to share some of our learning at Microsoft in the past over a decade exploring Gen AI for precision health. So I want to start with an observation. Let's see if the remote work. I don't think the remote actually work. Did I miss anything? 这个不 work 是吧？好 ，OK. So I want to start with an observation. So history has shown that technology can be the most powerful democratization force. For example, every one of us here have much better healthcare compared to any king and queen in the past. So it naturally begs the question, can we empower everyone in the globe to have the same kind of high-quality healthcare just like the most resource person like Bill Gates and Steve Jobs, right? In fact, we can be even more ambitious because, as we well know, today's healthcare is actually have a giant growth area. For example, Steve Jobs unfortunately still succumbed to his cancer. So we can actually ask, can we empower everyone in the globe to have better healthcare compared to even the most resource person today, right? So this whole talk is really just one long argument to say this is not completely crazy to think about these two goals. In fact, with the progress in Gen AI, arguably we're already knocking at the door. Now, before I dive into the detail, I want to also add a disclaimer. We are still very early. So some people liken this to be the moment when we first discovered that copper wire can actually conduct electricity. So on one hand, we are still searching for the equivalent of the light bulb. On the other hand, we also have to be careful because we don't want to actually conduct the equivalent of electrocuting people. So at the beginning of the sort of like technology transformation, oftentimes the natural instinct is to shoehorn the new technology into the existing workflow. But arguably, actually, the much better kind of potential would be to reimagine the entire new workflow, the new ecosystem, the new business model, and so forth. And again, we are still very early. So our overarching research program can be thinking about as learning the language of a patient, right? So for example, a cancer patient may have CT, MRI, digital pathology, multi-omics, and each modality is screaming at us about the patient. But if we don't understand the language, they just sound like gobbledygook, right? On the other hand, if we can master the language, then we can start to progress towards this dream about the virtual patient, where we can actually simulate all the multimodal longitudinal patient journey, and then begin to be able to accurately forecast what will happen to the patient next. Now, of course, AI is very exciting, but AI is no magic, right? So sometimes AI may appear magical because you apply the right algorithm to the right data. And in biomedicine, the really exciting thing in the past few decades is the rapid digitization of biomedical data, right, as you well know. So from genomic sequencing to electronic medical records. For example, every day when you think about it, there are literally billions and billions of data points documenting the journey of a patient from diagnosis to treatment to outcome. If we can crack the code and distill the insight, this will essentially become a population-scale free lunch, right? And so now, obviously, this whole field about real-world evidence or RWE is not new, right? So insurance companies have been milking the claim data for decades. But in the past, what have been limiting is that typically exploration is on the available structural information. And that means vast majority of the patient detail. Like, for example, for cancer, right, you don't actually get mostly the detailed information about the health status, prior treatment, staging, even cancer recurrence, you don't typically get in the code, right? So here the really exciting opportunity is that with the Gen AI, the much more powerful tool, we can start to understand, make sense of all those kind of really messy, really high dimension unstructured data. So to make our discussion more concrete, let me show you two examples to showcase what are the opportunities and challenges. So as many of you know, in cancer, unfortunately, standard care often fail, leaving clinical trial to be the last hope. However, actually only a tiny fraction of patients were able to find a matching trial, whereas ironically, many trials fail because they couldn't find enough patients in time. So as you will see later, this is actually a marquee example where we are already, even with the existing Gen AI, we are already capable of doing a major transformation to make much bigger progress. Now, another example is immunotherapy. So as many of you know, right, in cancer treatment, the first generation, we basically slash, poison, and burn. In traditional chemo, we just kill all the dividing cell. It's not very satisfying, right? So then we move to the second gen targeted therapy. You develop a guided missile to neutralize the mutant protein domain, right? Now, for both of this kind of cancer treatment, the challenge is that the response has not been durable, right? So cancer is blessed by the natural selection, so oftentimes come roaring back after a while. Now, immune system is actually the one health system that also blessed by natural selection. So it basically hold a promise that to be able to tame cancer once and for all, right? So indeed, you have seen some of this kind of breakthrough, like Keytruda, like checkpoint inhibitor, that actually can work miracle on some of the late-stage patients. Now, overall, however, we are still very, very far away from cracking it, right? So majority of patients still actually don't respond. So this is actually a marquee example where there is so much potential that we can go. So when we think about medical discovery, we often think about the early R&D. Now, indeed, they can be quite exciting and foundational, but in the grand scheme of things, they're just a minority of the cost, right? And also, even if you got the perfect kind of like candidate, it still takes years to validate. Now, the actual immediate transformation opportunity actually lies in the later, much more mundane stages like clinical trial development, the post-market studies, and so forth. And they also tend to be actually the marquee application area for real-world evidence. Now, so this is exciting, but can Gen AI deliver, right? So these days, there is obviously lots of hype, but also lots of skepticism, so it can be a little bit confusing. So I find it very helpful to think about Gen AI application in biomed, kind of spanning this spectrum from like productivity gain to creativity gain, right? So on the left-hand side, this is where human experts are perfectly capable of doing it, but they're just so slow, tedious, and expensive, right? But this is exactly a sweet spot for Gen AI to already start actually helping. Now, on the right-hand side, obviously, we're still very far away from scaling the kind of like automating discovery to scale creativity gain, but those are really exciting moonshots. And then at this moment, we should really remind of the Amara's law, right? So we typically overestimate the short-term progress, which lead to all the hype. But at the same time, we also tend to underestimate the long-term progress, even though the major transformation already happened. Now, in AI biology, right, one of the really exciting opportunities that already start happening is the clinical trial matching, right? So one of the big bottlenecks to match a trial versus patient lies in all those unstructured data about the patient. So here's the identified journey of a cancer patient where each bar is basically one clinical note. So as you can see, there are many, many node types, and each node actually contains tons of information about the patient, but it will take a long time for a human expert to actually go through all those nodes, right? Traditionally, when we try to use AI to do this problem, right, we will say, let's pick an attribute, let's build an AI model to try to extract those attributes from the text, right? So this is fine if you have just one attribute to tackle, right? But very quickly, you get into this, what people call the death by dozen cut problem. So because the attribute we need to get out from the journey is not just 1 or 2 or 10, right? It actually can be hundreds, if not thousands, right? Now, what's amazing here is that the frontier model, for example, like GPT-4 or GPT-5, is already capable of extracting all those kind of information from those nodes, right? And actually perform both match or even outperform traditional, like one attribute at a time kind of supervised state of the art. In fact, this is actually applicable not just for easy stuff that you can do with regular expression, right? It's actually equally applicable to very complicated attribute like clinical staging, right? So there are this 600-page book, AJCC, documenting for each cancer type. Here are all the instructions you have to follow to determine whether this is like 2B or 3A, right? And remarkably, you can basically ask the frontier model to read the freaking manual, right? So put the instruction into the prompt, and then put the kind of the medical records, and the frontier model are already capable of following those instructions to actually determine the staging, right? So here's one example implication. Every year, there are 20 million new cancer patients in the globe. Traditionally, you hire this medical abstractor, it takes hours and hundreds of dollars to actually curate information for a single cancer patient. Now with a frontier model with GPT-4 or GPT-5, right, it takes seconds and costs you a few cents, right? So that means that we can now actually be able to having this frontier model just like reading all the nodes as they come in, right? Structuring all those information, and then you can basically do this just-in-time clinical trial matching for all the patients across all the trial at all the time point, right? You can factor in all the latest changes for the patient. You can factor in all the change in the research protocols and so forth, right? Which in the past you can't even get through a tiny fraction of that cross-product. And we are very lucky to have amazing collaborator in Providence Health and to demonstrate that actually this can work already end-to-end, right? And what's exciting is that this is not just limited to clinical trial matching, right? Because if you have this technology and capability, you can actually start to reimagine the entire clinical trial process, right? And traditionally, there are so many steps in the clinical trial, right? Each step can take a long, long time. There are so much friction in the whole process, and that's why a single cancer trial can cost upward of $100 million, take years, and often can fail even before you can gather enough evidence. And now with today's even just today's Gen AI, we now have the potential to actually start to reimagine this whole process. And one of the really exciting opportunity is to democratizing access to clinical trial, right? So even in the US, right, so there are 85% of cancer patients actually are treated in this community and rural hospital. They don't really have any trial coordinator to look for the trial for them, right? So the life and death could be just by zip code, right? And now you can imagine actually having the AI to actually structure all the information for everybody, right? And now, on one hand, patient could potentially find life-saving trial. On the other hand, you can now get much more representative population into the trial, and then you can finish the trial much, much faster. So that's very exciting, but we are barely scratching the surface, right? So far we showed that how frontier models are very good at understanding and reasoning with natural language text, including biomedical text, right? So I make my first half of my career as a biomed NLP person. Some of you might have used our PubMed or BioGPT stuff. But when GPT-4 came out, I know my job for biomedical NLP have been replaced, right? So they are just very, very good because there was so much biomedical text in the web, right? So PubMed, 30 million paper on the web. You have all the WebMD pages and so forth. However, text is only imperfect kind of human translation of all those information from the original census, right? So, for example, over the years, I have made a lot of friends. My radiology friends will start telling me that they sometimes don't agree with themselves 2 weeks ago, right? Looking at the same image. My pathology friends will tell me if you turn the slide 90 degrees, sometimes they will see different things. Now, this is very understandable. Those patterns are very complicated, right? Our visual cortex are not involved in the jungle reading MRIs, right? So then really naturally back the question, can we empower those human experts to be able to understand those secrets in those images, multi-omics, longitudinal records, and so forth, right? Now, these are actually the area where frontier models start to stumble. Simply because you don't really have that much multimodal data in the web, right? So when you actually test even the best frontier model on those multimodal, like medical imaging, like omics and so forth, they actually don't make a whole lot of sense there. So moreover, not only we need to empower the AI to be able to understand individual modality, right? We also need to understand the crosstalk across those modalities. So each modality is kind of like language, right? So your CT could be Chinese, right? Your pathology could be Hindus and so forth. And each modality actually sort of like is inherently limited, right? So we have to actually really synthesize all those modalities to be able to actually recapitulate the holistic patient. So no doctor, even the best doctor, right? They cannot even really internalize even a tiny fraction of 8 billion people's patient journey. But now we can start to imagine, can we using Gen AI to empower them to do exactly that? And this is really the ultimate kind of like moonshot of the creativity game, right? Now, obviously, we're still very, very, very far from that, but there are some promising kind of progress. So to actually sort of like think about how do we tackle this problem, right? So I'm a machine learning people, so this is my nerdy way to think about what is precision health, right? So your input is basically this multimodal input information, and then you just need to predict two things, right? Number one, the disease progression, for example, how will the cancer progress, right? And number two, what's the counterfactual treatment response? If you can actually forecast those two medical events perfectly, you are golden. Now, obviously, this puzzle is not so easy, right? So a patient journey is not a single snapshot, but actually a longitudinal journey. Moreover, most frustratingly, right, most of the information you want to know is not there. And even for the information that you observe, they have lots of biases, right? There could be lots of non-random missingness and so forth. But this is exactly why Gen AI can be so promising because the gen in the Gen AI is meaning a generative model. So that's basically a probabilistic concept that means that we basically try to model the entire joint distribution of all those clinical variables. So it sounds like we sign up for a harder job, but actually sometimes try to do the harder thing actually give you a much bigger reward, right? In particular, by doing this kind of joint modeling, right, you now have a principal way to compress all those observed information into this compact patient embedding, right? And then you can basically conduct a standard probabilistic inference by conditioning on the observed variable to infer the missing information. And then those holy grail kind of future medical events are basically a special case. So this basically inspires us to imagining, can we actually start pre-training a powerful frontier biomedical models from the real world data, right? And the Gen AI disruption means that we now, at the first time ever, start to be able to imagine that we can actually create this kind of high fidelity digital twin, right? That can actually really model the patient. Now, with such a digital twin, what you can do is that at test time, you can basically do this patient-like-me reasoning at the population scale, right? So, for example, for anybody who have a loved one who have cancer, right, the first thing, if you have resource, the first thing you do is try to find a second opinion. Now, if you have this such a virtual patient as a digital twin, you can snap your finger to find 1 million second opinion from the population, right? You can gather all those similar patients and interrogate what has happened to them, what treatment have been tried, and what's the longitudinal outcome. Is the side effect worth it, right? Is the gain extended survival worth it? So you can start to immediately improve patient care. But you can also start to interrogate, compare the non-responder versus the exceptional responder, and start to poke at the history, why those 80% of people don't respond to checkpoint inhibitor, right? And in LLM, many of you are probably familiar with this concept about emerging capability, right? So that basically means that if you have a large enough capacity of model, you consume large enough of the data, then the models start to actually attain capability that you didn't even imagine they could do at the beginning, right? So now you can start to imagine, what if we are able to actually train enough high-capacity model to consume all 8 billion people, right, patient journey, to start figuring what kind of capability can we unlock, right? That can potentially shatter today's, even the best healthcare glass ceiling, right? And to actually get to the places where even the best doctor have no idea. So obviously this is not so easy, right? So, there are so many of these modalities, and as we already talked about, right, so the frontier model are not very good at all those non-text modality. And also, many of these modality, right, so some of the speakers will talk about like spatial, single cell, and so forth. By definition today, they are very scarce, right? So you can't really do the brute force to actually try to learn from them. So in case you haven't noticed, I'm a firm believer of free lunch, right? So actually every day we are just thinking about is like, what kind of recipe can we actually find out a free lunch, right? So I summarize them into 3 recipes. So the first recipe is actually the so-called unit model self-supervised pre-training, right? So the idea is actually very simple. Many of you are familiar with this paradigm. You basically introduce a modality-specific encoder and decoder. You're using an encoder to compress the original data point into a compact representation embedding. And then you use a decoder to reconstruct the original input, right? So in this way, you can basically convert any unannotated data point into a self-supervised training instance. So if you have an image, an annotated image, an annotated protein sequence, you can basically convert them into a self-supervised instance. And also for the text, somebody already spent billions of dollars, so you don't have to do anything, right? So this is a very powerful paradigm, but for individual modality, there are still lots of challenges, right? So for example, we talk about the digital pathology, and many of you know that that actually is lying in a lot of secret about the tumor microenvironment that govern whether a patient will respond to immunotherapy, right? And so, and if we can actually really understand how those immune cell and tumor cell actually interact, right, you can figure out the grammar, then you can potentially crack the code for the precision immunotherapy. And in principle, transformer is actually exactly the right tool to do this, right? So you can think about transformer essentially for image. It's like you're trying to do message passing between every 2 pair of pixels, right? The layers are basically you do it message passing for many rounds, and then every pixel know every other pixel. So in this way, you can capture arbitrary complex global pattern. And that's why transformer is such a workhorse of the modern Gen AI and so powerful. But transformer have one Achilles heel, right? So by doing this pairwise message passing, that means the computation scale actually quadratically to the input. And unfortunately, pathology slide is one of some of the largest image in the world, right? So each of them can be 1 billion dimension, right? A single pathology slide, if you use a standard transformer, it can cost you billions of time of compute compared to standard cat and dog images, right? So what we do is that we basically steal an idea from speech recognition called dilated attention. The idea is actually very simple, right? So you can afford the quadratic in the local neighborhood by passing messages in your neighborhood so that everybody know your neighbor, right? The challenge comes when you try to commit a message from a local neighborhood to a faraway neighborhood. That's what kills you. But what you can do is that because each neighbor already know, each pixel already know the neighbor very well, so you don't really have to communicate the message for every pixel, right, to the remote neighborhood. You can just pick some representative for each neighborhood and then let the representative exchange the messages. So this is literally the idea. So, and we are very fortunate. We have great collaborator from Providence to University of Washington. So last year we actually come up with this first kind of like digital pathology foundation model that can truly scale transformer to gigapixel pathology slide. So the paper was published in Nature. We're grateful about that. One thing that we uncover is that we throw some really hard problem at this GigaPath foundation model, right? We try to say, can you find any pan-cancer signature across 31 cancer type, right? And that correlate with some of the biomarker, important biomarker status. And surprisingly, it actually were able to find some of those very strong correlation that our collaborating pathologists have no idea about, right? So this is kind of like, obviously a tiny, tiny baby step, but sort of give you a glimpse of what kind of discovery beyond the human expert can look like. So very, very excited to see the community have so much interest in the model. And some of the researchers actually in Mount Sinai and MSK, Memorial Sloan, actually conducted a prospective global trial that showed that they can fine-tune GigaPath to actually use in actually clinical deployment. So seeing this Nature Medicine paper really made my day, right? So basically our dream is to be able to actually start to go into some of those end-to-end deployment. So this is very exciting, but learning those individual modality is just the beginning, right? So again, like those modality, each modality is like a distinct language, right? And we are still facing a United Nations problem, right? Because each language, each modality in a distinct language, and they don't understand each other. So in actual machine translation, what do people do? They basically introduce a resource-rich language like English as an interlingua to bridge across all the different languages, right? So for example, you can translate from language A to English and then from English to language B. That's essentially how Bing Translate or Google Translate actually scale to hundreds of languages in the world. So what we actually propose is to steal this playbook, and then the natural modality is obviously the text, right? We already have very strong foundation model there. And there are also the second source of free lunch, because there are lots of, for each modality, oftentimes you leave a paper trail. You have some caption or reports or what have you that actually give you some information about the image, right? That you can leverage. So what we actually propose here is that we can build on top of the first stage, learning those, reusing those, starting from those encoder and decoder, and then focus using those free lunch to train this very lightweight adapter as a translation layer, right? So I wouldn't belabor you about the detail, but point you to the LavaMap paper for example recipe. With using this recipe, we were able to train this biomap parse model that unify 9 image modalities, 64 object types. So I'm a lazy person, so I always dream about, hey, can I talk to the model to let them do all the work? And we start to see that happening, right? So very excited, exciting. So again, very excited to see the community interest. Very grateful for the paper to be published in Nature Method. They also publish an independent external review that says some very encouraging word for our paper, so we're grateful about that. So far we talk about the 2 free lunch, but there is one last, but actually the largest final free lunch, right? So when you think about what is a GPT-4, it basically learns by predict next token, next token, next token. Now, virtual patient can actually essentially do the same way by predict next medical event, and so forth, right? So obviously, if you just train on 1,000 patients' journey, nothing much happen. But what if you can train on 100 million patients' journey? Then something interesting start to emerge, right? Now, of course, before you do that, you have to be careful about how do you actually optimize your compute and so forth. So we conduct some of the first, among the first scaling law study for structured patient journey. We are very excited to collaborate with Epic Cosmos to actually train the first population scale structured patient journey foundation model on 300 million patient journey. right? So very excited to see that coming out of the world. So in the long run, right, so we want to really think about not only embedding patient, but can we also embed intervention, drugs, and so forth. Some really exciting progress. In the interest of time, I skip them over, right? There are reasoning, for example, multimodal reasoning is a really hot topic. Everybody thoughts about agent, right? So one of the really exciting prospects is that in the future, there may be a single person running a unicorn or a $1 trillion company, right? And now, before we get there, right, obviously we also have to develop lots of stuff. For example, agent MBAs and so forth. We're far, far away from there, right? But there are already some kind of baby step that can be seen there. So I want to kind of end on a very sort of intentionally provocative example. With all this capability, what it means is that we can now drop any research protocol. You can conjure up a virtual case arm and virtual control arm, and then basically have a population scale hypothesis generation and testing playground. So to show that this is not completely crazy, right? So we work with our collaborators to show that we can actually using real-world data to simulate some of the marquee lung cancer trial and including the original Keytruda trial, right? So I want to thank all my teams, and also they do all the work, and also our amazing collaborator without whom we can't do any of this. Thanks so much.
Thank you. Thank you, Professor Fu. Because we are a little bit running out of time, we just have one question. Any questions? Maybe I'll ask a very general one. So I think it sounds very promising for the generative AI models, but I would like to know, like, what do you think would be the most significant bottleneck at the moment that limit the widely adoption of the generative AI models for biomedical research?
Yeah, great question. I don't think there is only one. I wish it's only one, right? But I would say that actually we often think about immediate kind of like clinical deployment, right? And like clinical decision supports and so forth. But that the bar is actually very, very high. Like from a computer science parlance, that's almost like you need a worst case guarantee, right? So if you have noticed, like a lot of what we focus on right now is on how can we empower like the clinical research and discovery side, right? Because in those cases, you basically summarize the population statistic. You just need an average case guarantee. Yeah.
Thank you.
Yeah, thanks so much. Okay.
Now let's welcome the second speaker, Professor Gao Xin from the King Abdullah University of Science and Technology. He will give us a talk on large language models in biomedicine. Let's welcome.
Okay, good afternoon, everyone. First of all, I would like to thank Dr. Qian Cheng for the very kind invitation. And I would like to thank the organizers and the Nanjing University for the great hospitality. It's a great honor for me to be here to introduce our work. So just give me 1 second to... Can you show my slides, please?